Hi, this is Yijia. Welcome to day 5 Origo's Whitepaper walkthrough. Thanks for keep listening for this series like talks. And today's topic will follow on yesterday's protocol details. So yesterday we talked about at the stage of like compute, and then we mentioned that in this stage, like each party open its input to executor, and then the executor need to generate a proof. And then we mentioned about the participant side that the participant need to send the encrypted data to blockchain, and the proof, a zero knowledge proof to the blockchain that the encrypted value match his commitment. And this is the reason we for that we talk about I talked yesterday. And also for the blockchain side, you need to record the encrypted data, and then need to verify the proof that the encrypted value match the commitment in last step. And also, I forgot to mention, is like you need to check the encrypted data received before the deadline of this open stage. So you you remember that we have like a several stage. So the first stage is like commitment, and the second stage you can think about that's like open. So and the third stage is like when all of the input data are open, then the third stage is like compute, right? But you cannot say, okay, you send the data when the compute begin, right? So it's like you have to send the data before the compute, right? So that's why the blockchain can ensure that the encrypt data received has a time, and then it need to be before the deadline of the open stage, right? So to ensure that, okay, if you don't open the data by that time, we can think you as a bot, right? So because you cannot say, okay, people are already start playing the game and then you join. That's not how it works, right? So the blockchain will also check the encrypted data received before deadline, and then send the encrypted data to off-chain executor. So we end of the calls like here yesterday, and today we're gonna continue on that. Also for the compute stage, when blockchain send the encrypted data to the executor, what does the executor do? So the executor receiving the verified encrypted data from the blockchain. So he knows that this data is not from like someone sent to him randomly. It's sending from the blockchain. So everything gets recorded. So the executor also like guarantee that he actually received this kind of data, right? And then he decrypted the data for computation. The reason that he can decrypt it is because the data is actually encrypted by his public key. So he can like decrypt it by using his like a private key. And if so, there's a stage that he will need to wait for all of the data to came from the blockchain, right? But if some participant like fail to submit the proof, or say the participant actually cheating, and then he submit a commitment first in the commit stage, and then he submit a proof. Say this is the encrypted data matching the commitment, but the proof cannot be verified. Say it's a wrong proof, it cannot be verified. So it's like a fail to submit the proof, right? Or fail to submit the encrypted data to the blockchain. They will be like considered as a bot to the game. So the executor knows that, okay, someone a bot. Okay, I will consider, okay, he doesn't send me any data. And you may think about like a malicious like a executor could on purpose like abort the contract. Say for example, you play rock paper scissors. Two people play rock paper scissors, and then the executor is a friend of like a user A. So by the protocol design, he cannot say before the commit stage telling like a user B A's choice, because when that happen, when the commitment happen, the executor doesn't get any information. So even he's a friend of user A, he cannot do that, right? But what he can do is like when the executing stage, then no one can actually change the input, but he can abort. Say he when after he execute the rock paper scissors, he find out okay user A will lose, and then he say oh okay I don't want to do the game, I don't want to do the execution, and then he will abort. In order to to actually reduce the chance of that, we need the executor to put a deposit. So if he fails to let's say he fails to run the execution, he don't want to prove he don't want to run it and then generate proof, he will lose the deposit. So it's like an economics way to make sure that he actually run the stuff. So then you can actually lower the chance of that. So that's the compute stage. So it's more like the executor getting off the data and decrypt the data, and so it can behave as a validator, a normal validator on Ethereum, and do the work. But the only thing different is what we mentioned later. It's in the settle stage. You need to generate a proof. So in the settle stage, the executor need to submit the result and a zero knowledge proof to the blockchain, and the smart contract or the blockchain need to verify the result is correct by verify that proof, and the blockchain distribute the token to the parties. Okay, here's the detail. It's like the executor after execution the contract, the logic, he will get a bunch of results, right? And you can think about it as outputs. For different participant, the outputs could be different because, like say, for like a rock paper scissors game, the winner will get money, and then the loser will get zero, right? So it's like in order to protect the outputs, to keep the privacy of the outputs, then all of the output for the each participant will be encrypted, say by the party's public key. So say it could be like an encrypted output 1 to like an encrypted output n, and the executor also need to do is like send the encrypted outputs with the proof to the blockchain. So it's like so the blockchain get the encrypted outputs and the proof. It's a zero knowledge proof. So people see on the blockchain is okay. There's a bunch of like encrypted outputs. I don't know what's the detail for that. And here is a proof which has zero knowledge of the execution. And the blockchain can verify the proof to check the contract is executed correctly. So after he like verify this after the blockchain like we can select a bunch of nodes, make a consensus on the proof and verify the proof, and then it makes sure okay this work is done correctly, and then this for given, and this output is correct, and then the blockchain will try to distribute the coins to each party based on the execution result. I will mention about the coins later for the for private transaction. So yeah, the blockchain do is verify. If it's correct, okay, I will finish the distribution. And what participant do is like okay, I know this is the result after verified by blockchain. The result is final, and I can decrypt the outputs. So because the outputs is actually encoded by my public key, so I can like decrypt it, right? And if he get any coin from the contract, he could like deposit to his like wallet using the private transaction. So it's like the coins actually when you finish it, the coins it's distributed to some parts, also like associated to the contract, and he could like withdraw that, right? So it's more like a logic for the private transaction. If it doesn't need to like protect the outputs, then the blockchain can distribute distributing the money or like the token directly. But if you want to keep the outputs and also the transaction to be private, then this is the logic there. So it's more like I will like rephrase, resummarize the saddle. The saddle is like the executor encrypt the outputs and generate the proof. Given that to the blockchain, blockchain verify, okay, this is correct, and then okay, then this output I think is correct. I guarantee is correct, and then I will tell the participant, okay, that's the final result, and I will distribute the coin based on this final result, and the participant can decrypt the outputs by his like a private key, and he can withdraw the money from the contract using like a private transaction stuff. Okay, then we mentioned a lot for like input outputs, but let's talk about the transaction privacy. Because think about like for Ethereum, if we only import, we can also like implement this like protocol. That's what we currently doing, but it actually missing the transaction privacy. So you know, okay, the detail of the execution is like a private, but all of the transaction are public. You can keep the input data as private, but like you cannot keep the money transfer as private. So that's why we want to implement this kind of transaction privacy. So we will maintain both like a public ledger and the private ledger, which is similar to Zcash, and we use zero knowledge proof to ensure the privacy of ownership of the private coins, and the sum of the input value equals to the sum of the output value. So which is similar logic to Zcash. So for the private coins, a user has three actions. So the first one is mint. So mint means that it allows the user to convert like a non-anonymous coins or anonymous tokens to a new coin. So in this way, it's more like, okay, I can transfer like a public one to a private one. And then it hides both the coin's value and the owner's address by using commitment schema. So it's more like I put up some like coins and then using like commitment method and then say this is the coin. And if I bring out the proof or bring out the information matching the commitment, then I can prove that coin actually belongs to me. In this way, it's like making the coin private. It's similar to it's actually Zcash's method, and the pool action is like allow the user to make private transaction by consuming the private coins and produce a new public or private coins. So it's more like a withdrawal. You can think about that's like a similar like a withdrawal, and those are the two actions actually, yeah, actually similar to Zcash, but we have another action because Zcash doesn't have like a smart contract, so this is more like an action associated to smart contract. It allows the user to remove one of his private coin and freeze it to contract. It's more like you put the money to the contract so you can run the smart contract, right? So, and also you can use this option to make the private deposit to the contract. So it's more like, yeah, you can think about it's like a mint to contract. It's not mint. It's different action. It's more like a transaction supported natively by a blockchain to allow the user make a private transaction to the contract. So it's like the contract can hold the money, right? So these are the three actions for transaction privacy. So yeah, that's probably today's course. We like finished the detailed protocol of our like protocol, and also we mentioned that we need to support like a transaction privacy to actually have this whole stack, like the whole scenario, hiding the both input, output, and also the whole transaction step. Yeah, and tomorrow I may talk about our like scalability design or scalability thoughts. Yeah, and thanks for listening, and which the yeah